Okay, let's get back into business. Everyone survived the first half of a lecture? Let's see if we can survive the second half. Okay, so if you haven't signed the attendance sheet, it's up here. You can sign at the end. Okay, so any questions on the first half? No questions, so everyone got it 100%, correct? So I see people taking photos of this. What if I told you that I will be giving all of these to you, all of them, for free? Okay? You can take photos. I don't really care about that. Okay, any questions though? Okay, super. So let's actually look at one of these machines. And you'll think, okay, Ryan, this is super easy. Why are we even looking at this? So we got to start somewhere. We got to start at the most basic level possible, okay? So let's look at a two-state machine. Not billions of states, just two simple states, and that's it. So here's the machine that we're going to look at. And I'll explain all of the notation in gory detail in a second. And there is our humble machine, machine numero uno. Okay, so what in the world is this machine? The circles here. So all of the circles, so Q0 and Q1, ignore the outer circle on Q1 for now. Just the circles, those are states. So each one of these, so these are states of the machine. So is Q0 a state? Yes, because it's encased in a circle. Is Q1 a state? Yes. So, okay, so that's fine. What are these arrow things between the states? So what are these arrow things? These are transitions. And then you may say, my watch thought I saw said, hey, Siri, okay? So it recorded everything I just said and tried to make a search off of that. All right. So you may think, okay, these transitions, I see one between Q0 and Q1. It has a certain label on it. And the other direction, it also has a label on it. You mentioned, Ryan, before that the transitions between the states on a computer correspond to executing an instruction, right? And I'm pretty sure, but I think 0 is not an instruction of a computer. Is 0 an instruction of a computer? A real instruction that you would run on your x86 processor. Is 0 an instruction? I mean, a bunch of zeros might be, but just a single 0. No. So what is the beauty of this class again? Abstracting the details. I don't care what the instruction is. I just simply don't care. If I see a 0 on the input, I'm going to execute that transition. So if I'm in the state Q0 at any point, and I see a 0 on the input, what state am I going to go to? Q1. If I'm in state Q1 and I see a 0 on the input, what state am I going to go to? Q0. I know it sounds tedious, but it's important. Okay? Does everyone understand the transitions between the states? I'll get to the other stuff in a second. Yeah?
Would it be incorrect to call the transitions input since it goes from one to another, or is that something?
You can call them inputs, yeah. I'm going to use the term transitions. So sometimes I'll use on input 0 from state Q0, we go to state Q1. Okay? So, but you can think of inputs, transitions, exactly the same. Because each of the transitions has a single character label on it. Any other questions about the transitions? So, what do you think this arrow is that's coming from nowhere going into Q0? What do you think that represents? The start state, right. So we got to start in some state. And because computers are deterministic, we can't start in any number of states. We got to start in exactly one state because computers are deterministic. So I picked Q0 to be the start state here. Can Q1 be the start state possibly? Could I arbitrarily just say, set that arrow to point to Q1 instead? Could I do that? Would it change the behavior of the machine though? It might, but am I allowed to do it? That's the thing. I'm not getting an enthusiastic yes or no. Who votes yes? Could I do it? Who votes no that I can't do it? Okay, so it's mostly yes. All right. So I could set Q1 to be the start state, but I am setting Q0 to be the start state. And only in exactly one of these states will get this arrow thing. Okay, and then the final thing is, what does this double circle represent?
Accepted state?
Yeah, so accept state. So remember from before we said all of the states in our machine could be set to 0 states or no states, or they could be 1 states or accept states. So the double circle here means accept, or quotes yes. So if we end up in this state, then we say yes. Question for you. Because computers are deterministic, if I'm in Q1 and I still have input left, can I say yes right now? No, because computers have to do the exact same thing every time. If they see something on the input, they have to proceed because they're deterministic. Okay? So for that reason, if we've run out of input entirely and we're in Q1, can I now say yes? Yeah, because I've run out of input. So that's actually another thing that we're going to consider in our model. Let's just say that in your computer program, I provide you a string. Could you go back and forth across that string as much as you want? If I give you a string of characters? Could I set a for loop to go forwards and then another for loop after it to go backwards? Could I do that? Yeah. So what we're going to do in our model is to make things a lot easier. You can only go forward in the input and never go backward. So what happens as a result is, because we can only move forward, if we've consumed a character, is that character essentially never going to be seen again? Yeah. So we're only going to move forward through the input. It makes the analysis a lot easier. Okay? We're trying to make this as easy as possible. Okay? So we're only moving forward through the input. So let's actually model what happens on a particular input, because it'll motivate the formal discussion later. So what is a possible input to this machine? Could I provide the input 111 to this machine? No, why not? Oh, there's no transitions anywhere in the machine labeled 1 out of a state or something. So what are the possible inputs for this machine from any state? 0. Here's another thing. Suppose that our inputs could be a 0 or a 1. Could Q0 have a 0 transition but not have a 1 transition? Because computers are deterministic? No. So in fact, every state in the entire machine must have all possible outputs that they could conceivably have. But could a state, for example, have, say, Q0, have 2 outputs labeled 0? Could a deterministic machine have something like that? No, because now it has to make a choice, right? I don't know which one I'm going to actually do. Could a machine have a 0 on one transition and a 1 on another? Yeah. But could it have no transition labeled 2, for example? Am I allowed to have that? If the input could have a 2 in it? No. What if the first character is a 2? What do I do? It doesn't know what to do. So I have to provide for every single state everything that could possibly happen. We'll have ways of saying, this is an unwanted input. Do something with it. We'll have ways of dealing with that. But for now, we have to have every transition of every possible input present. Okay, so let's look at a particular input. So can someone give me an input, a valid input for this machine? 1010, is that a valid input for this machine? No, what is a valid input for this machine? 00. I'm actually going to put another one. It fits with my notes. Okay, so when I turn on the machine and I have not done any computation at all, I just turned on the machine, what state am I in? Q0. Why? Because that's the labeled start state. Good. So I'm going to model what state I currently am in. So I'm in Q0 right now. I have not read any input. Are we good? I know it's tedious, but it'll make everything else easy. All right. So now I'm in Q0, and I have read one character. There's only a 0 here to consider. But what state am I in after reading that one character? Q1, because I just followed the transition labeled with that character, and then after I'm in Q1. Perfect. So now at this point, what state are we in? We're in Q1 right now. So do we have more input to read? Have we exhausted the input yet? No, we have not read all of the input yet. So what do? Help me along here. I keep going. So what do? What character do I read? The next 0. And what state do I end up in as a result?
Q0.
Q0 again. Cool. So we've exhausted that character. Are we done reading the input yet? No. So what do? We go back to Q1 after we consume the next character. Are we done exhausting the input yet? Yes, we are. So did we land in an accept state or did we not?
Yes.
We did. So what do I say on input 000? We say yes on this input. So we say accept. If I can write accept. If I fed you the string 00, which has two zeros in it, what would you say on that input? No, or reject, or whatever your favorite word is. Here's another thing. Could I have said Q1's not an accept state, neither is Q0. Neither state is an accept state. Could I do that? No, I'm not asking whether it makes sense. Could I do it?
Yes.
Yeah, I could do it. It'd be a pretty dumb machine at that point. I'm wasting a state, but am I allowed to do it? Yeah. So I can have any subset of the states correspond to accept states. Okay? As long as it's a subset of the states, we're okay. Let's do a more complicated example. Or are there any questions about this example? Let's do a more complicated example with 4 states. And then 8 states, and then 16 states, and then you know what happens after that. So I'm going to have 4 states, zeros across on the top and on the bottom. And then 1s on the up and down between the 0 and 2, and then the 1 and 3 state. So I claim that this is a deterministic machine, where all the inputs could be a 0 or a 1 at any point. So this is something that unfortunately happens. A professor comes up and tells you something, and then you have to make the choice of whether you believe it or not. So this is something that is called proof by intimidation. So let me try not to intimidate you and not lead you down the garden path with this. So is this a deterministic machine?
Yes.
It's not me just telling you this. Is this, in your opinion or your observation, is this a deterministic machine?
Yes.
Yeah, why?
It has all the inputs and outputs.
Well, let's see. Let's look at every state. Does it have a 0 leaving it and a different transition labeled with 1? Well, look at Q0. It has a 0 going across, 1 going down, 1 same idea, 2 same idea, 3 same idea. Okay, so that's good. What if the inputs of this machine could be 0, 1, and 2? Is this a deterministic machine?
No.
No. So it's important to set at the very beginning what are the valid inputs to the machine. Because one set of inputs could be valid and then the other one might not be. So if the set of inputs that could be here is 0 and 1, we're okay. No problem there. So let's see. Can anyone give me a string that is accepted by this machine? Any string at all? Yeah, 0 is 1. What's another one? 0, 1, 0 is good. So let's just make a list of some accepted states, strings. So 0 was accepted, 0, 1, 0 is also accepted. Just one, and we can make an infinitely long list, obviously. What about rejected strings?
0, 1.
0, 1's example. 1, 0. Let me write one for you. Ooh, what's that simple? Anyone happen to know? Epsilon. So yeah, so you're actually correct on that. It's actually the string with no characters. So let's look at the empty string here. So the empty string is the unique string without any characters in it. Okay? Well, is the empty string accepted by this machine? No. What state do we end up in after reading the empty string?
Q0.
Yeah, Q0. We don't go anywhere because we don't. Well, first off, there's no transition labeled epsilon here for reasons we'll get to. But more importantly, because the empty string has no length and going across a transition involves consuming a character, empty string has no characters, so we can't execute a transition. So therefore we are stuck in Q0 and therefore we are not accepted. Cool. Let's go back to this machine for a second. The 0, 0 machine up above. Can anyone give me an English description for what strings are accepted by that machine?
Odd number.
Yeah, odd number of zeros. Anyone disagree? Yeah, and we can actually prove by induction that it is. Well, the string of length 1 goes there, and every odd length above a certain number is because we can just do however many transitions we need to do, and then one more back, one more forward. And then the even length strings are not because we always end up at Q0. In fact, the name Q0 represents the modulo by 2, so the parity of the length of the string. So if we take a string of length 100 and modulo to that, what is 100 remainder 2? 0. And so therefore we end up at Q0. So the name actually is kind of helpful here. By the way, you may be wondering why states are named Q whatever. That's actually just purely tradition. I have no idea why they're called Qs, whatever. In fact, a better name would have been S something for states, but Q is just the name that was picked. What about the second machine? Anyone happen to know what that is? Yeah.
They accept odd number of zeros or
odd number of zeros or odd number of ones, I'll disprove that. Pick any string with an odd number of zeros and an odd number of ones. That has even length.
0.
Yeah, 0, 1, for example. And then we'll end up in Q3 as a result.
Sum of zeros.
So that's one formulation. So the number of zeros plus the number of ones is an odd number. That's another way to look at it. Yeah.
Odd number of zeros or odd number of ones, but not more.
Yeah, so that's another formulation. Here's a much easier formulation. Odd length strings. But what is the difference between these two machines? What does the first one have that the second one has that the first one doesn't? It has ones on the transitions. So could we actually make this second machine simpler than the one that's here with 4 states? In fact, we can. So we can do something like this. And then that works. It's exactly the same set of strings. These two machines accept the same strings because they do the same thing. So you may be wondering, okay, Ryan, what is this comma right here? So this comma represents multiple transitions. So it's not the transition labeled 0, 1. It represents a transition labeled 0 and another transition also labeled that's labeled 1. And then the same idea in the back direction too. So these are 2 examples of this deterministic machine. Any questions on these? Cool. Is this formal? This picture right here, is that formal? So this Q0, Q1 one, or this 4-state one, or this 2-state one down here, could I present this to a computer and say, compute it on this string? Could I present that picture to that computer? What does it need? It needs a specification to say, here are the exact state names. Here are the characters that are allowed on the input. Here are the transitions. Here's the start state. Here are the final states, provided as lists or whatever. But it's provided in a formal way to the computer. And then the computer, upon receiving those 5 bits of information, goes, now I know what deterministic machine you're talking about. Okay? So do you think there's a reason why we should care about formalisms? Maybe you don't, but we'll get there. All right. So, but mainly the reason is that you could be talking about, so in fact, the interaction that we just had where a student just said an odd number of zeros or an odd number of ones, but I gave a counterexample. But the student probably thought an odd number of zeros exclusive or a number of ones. Is that the case? Say yes. Okay. Yeah. So there's a problem here. English is extremely informal. So I could be saying something to you, and then hopefully you understand, but there could be some miscommunication here because you grew up in a different background than I may have. I may say things in a way that you might not understand. English is a terrible way of communicating formalisms. So we need a formal specification that is unambiguous here. So what do we want? We want a machine that's deterministic and has those 5 parts that I mentioned before. So let's get right into it then. So a deterministic finite, and I'll get to that in a second, automaton, or a DFA. So we're pretty much going to say this the rest of the class. If I'm going to say the acronym DFA, what does that correspond to? DFA.
Deterministic.
Deterministic finite automaton. Okay? We'll have a lot of three-letter acronyms in this class, TLAs. So, anyone get that? It's late, I know. Okay, so a deterministic finite automaton is what? We need to specify 5 pieces of information: the states, the inputs to that machine, the transitions of that machine, whatever start state of that machine is, and whatever the final states are of that machine. So is a 5-tuple, and then we're going to have 5 names: Q, sigma, delta, Q0, and F. Where? So 5-tuple just means 5 pieces. That's essentially all it is. Where, and then we got to specify various things on the 5 pieces. So let's see. I wrote finite here. First off, do you want to draw an infinitely sized DFA? We all have a finite amount of time, so we probably should work with finite machines, okay? But another reason is that if I allow you to use infinite sized machines, then that actually drastically changes the power of the model. So finite makes this a lot easier and is actually the right model to work with. So by that reasoning, should we allow you to have infinite number of states? No, we're only going to allow you to have a finite number of states. Any number that you wish, but some number of states. So Q is a finite set of states. Cool beans. What about, so Q is a finite set of states. Sigma is what? For each of the states, should I allow you to have infinite number of transitions out to other states? No, probably not, because then I have to actually take an infinite amount of time to figure out which transition I should apply. So sigma is a finite input alphabet. Should there be an output alphabet for this machine that we're talking about? Are we outputting strings here, or just going into final and non-final states?
Final, non-final states.
Yeah, non-final, non-final. So in fact, we don't need to output anything. So we actually don't have a output alphabet here. I'm actually going to skip over delta for now, and we'll come back to it because it's the most complicated piece. What do you think Q0 is? Is the start state. Well, let's see. Should it be a member of Q, the set of states?
Yes.
Yeah, that seems intuitive, right? But we provide you a set of states. Let's just say I provide you Q0, Q1, Q2 as the set of states, and I tell you Q3 is the start state. Do you think there's something wrong there? Yeah, so then you'll think, okay, what machine are you trying to tell me? So it better be the case that Q0 is a member of Q, is the start state. And if I go over time, please stop. I won't take points off or whatever. Okay, what about F? What do you think F corresponds to? Just intuitively. The states that are final, right? Well, let's see. Could it be equal to all of the states? In other words, every single state is final? Could that be possible? Yeah, it could be possible. Could it be that none of the states are final at all? So 0 states are final?
Yes.
Yeah, that could be possible. But could it be any subset of the states at all? Yes. So it could be any subset at all of the states. So let's just let F be an arbitrary subset of Q. Is the set of final states. So I'm going to tell you set of states, input alphabet, whatever the start state is, a set of final states, and then we'll get to transition in a second. But any questions on these four pieces? Yeah.
When you say when we said the set of final states, don't we have to specify what the final state is gonna output? If it's gonna be, could we have a machine that has a final state that instead of accept something, it's gonna say no to the input?
So the determination we made is that all accept states are going to be yes states. They're going to say yes, and all things that are not accept states are going to say no. So there's a correspondence.
So the finals are always accept.
Yeah. So final is always accept. Yes. And if you're not accept, you're always non-accept. Non-final. Yeah. Other questions about these four parts? Because the fifth, the transition function is going to be a little bit wonky. So let's see. So delta, what does delta do? So let's look back at our example. So let's just look at this Q1 right here. So how did we determine that it was Q1? How did we figure that out?
Current state and input.
We looked at the current state. Okay, so what was the current state in this case? Q0. What was the input character that we looked at to get to Q1? 0, right. So we looked at the current state that we were in and the input character, whatever it is, and then what happened as a result? What did it give us back?
Future state.
The state that we're supposed to go to. Okay, so think about that. An state and an input character together is going to yield another state, or maybe the same state, but a state at the very least. Okay? Any questions on that? Okay, so let's see. Well, we can think of transitions as just a function that take us from what? We got to provide a state and an input character, and it yields from those two things the next state. Well, what is the set of states here? Q. So it takes things from Q, and what was the character from? What set was the character from? From sigma, the alphabet, right. So we're going to think of these as ordered tuples. So, and if that made absolutely no sense to you, what should you look up? Chapter 0. Okay? Okay, so we're thinking of these as ordered tuples. So we're thinking of them as just pairs. Think of ordered pairs. So the first element of the pair is a state, and the second one is the character. Well, what is the transition function output? What should it give us back? What? State. What are states from? Q. Should I bar any state from appearing in either one of the Q places here? Should, like, say the start state not appear in any one place? No. I can have transitions from any state to any other state with any label I want. Okay? I'm not going to forbid you from saying transitions can't go back to the start state or whatever. I'm just going to allow you to do whatever you want with the transitions. Okay? Well, yeah, is the transition function? I'm not actually done here, but we're almost there. I promise. Well, let's see. It's a function, but does this guarantee that any state with any input character has a defined state to go to? And in other words, so think of like this example right up here. with the definition of the function, just a function as it is, could we have a situation like this, where we have an undefined transition out of a state? Yes, we can. I'm not allowed to have two transitions with the same label going out. I'm not allowed to do that because it's a function. But could I have an undefined transition? Yes. So how do we actually specify that? To say in the formal part that there's no undefined transition, whatever that may mean. So delta, we're going to have an additional specification, is a total function. And I almost guarantee you no one's ever heard that term. Anyone heard that term? Total function? Unanimous. So what does total mean? All total means is no matter what state and symbol you provide, the next state is defined. So this total business will forbade this situation from happening. We can't have a transition on a symbol and an undefined transition on another one. This situation cannot possibly happen because delta is a total function. Total function means no undefined transition. Okay? But we needed some way to specify that there is no undefined transition here. Any questions on that? Okay. So let's actually write one of our machines formally. So I'm going to harness the power of notability again. Hopefully I can get this good. God, I love notability. So amazing. Paste. Ah, yes. Do you make sounds when you do your homework like this? Whoosh, whoosh. All right. So let's actually look at this machine. So is this picture formal? No. So let's make it formal. So if I want to specify this machine formally, how many pieces do I need to define? 5 pieces, because DFAs are defined with 5 pieces. So what is a simple piece that we can define right now? The states, for example. So Q, the set of states, is what set here? So remember, it's a set of states. Okay? So I better write that it's a set because it's a set of states. What is this set as elements? Q0 and Q1, because they're elements of this set. Super. Here's a great exam question. Hint, hint. Can a DFA have 0 states? We have 1 yes? No? Anyone got a maybe? One of the least favorite things about being an instructor is when you ask a question, you get a yes, maybe, and a no. It's amazing. I love it. So we got a yes and a no. What is the true answer? No. And why is it no?
It's a 5 tuple, so it has to have Q0.
Ah, it has to have this 4th piece right here. Q0 is an element of the set of states. So does the empty set have an element in it? No, because it's defined to have no element in it. So by saying that Q0 is an element of the set of states, could a DFA have 0 states? No. So all DFAs have at least 1 state. Could they have 1 state only? Yeah, we could have transitions that go back to the same state if we wanted to. Okay, let's go back to our example. What is the input alphabet in this case? The only character 0. Could I have defined it to have other stuff in addition?
No.
Ignoring the picture. Just ignore the picture. Could I add more characters if I wanted to? Yeah. So as long as it's any finite alphabet, we're good. Here's a great question. And there's actually a bit of disconnect between what Sipser says and what is actually mathematically true. Can sigma be empty, have no characters in it? I'll let you think about that because it's actually a very interesting question. Whereas Q cannot be empty, but could sigma be empty? I'll let you think about it. But this one has 0 in it. So what is the start state in this machine? Well, it's Q0 because it has this incoming label to it. What is the set of final states here? Just Q1. So it's a set containing Q1 in it. So remember, Q, sigma, and F are all sets, all of them, all three. So if you're going to write them out, they better be sets. Okay? So now let's go on to the business of the transition function. So I'm going to show you a shortcut over just writing the transition function over and over and over. And it's actually using a transition table. And so what a transition table is to say each row corresponds to a state and each column corresponds to that input, and the entry of a certain row and a certain column corresponds to coming from that state on that symbol. Okay, so what do I mean by that? So let's write a table here like this with 2 rows because there are 2 states, Q0 and Q1. And how many columns are there? In other words, how many symbols are there in the alphabet? Just 1. So there's 1 column. So 0. So what do I put in this box right here? It's going from Q0 on input 0. And what state is that one in this case? Q1. Perfect. And what does the other box have? Q0. And that's all 5 pieces. So we have completely determined formally what this machine actually does. Oh, by the way, when I said total function here, all that means is that the transition table has no holes in it. So there's nothing blank in the transition table. That's an equivalent way of doing that. But we've specified this machine formally. We've written the states, the input alphabet, what the start state is, what the final state in this case is, and what the transition table actually is. Any questions?
So that's it.
Yeah, class over. Any questions? That's the complete definition of a DFA. There are other definitions, but I'm not done. I have 5.5 minutes. I will use every class all the time. So let's actually get some other definitions out of the way. So let's just let sigma be an alphabet. If I could spell alphabet. Well, we could talk about all of the strings that you could ever generate over sigma. So maybe 0, 1 is our input alphabet. You can think of all binary strings, for example. So basically, all strings that have a 0 or 1 in them in any place. Okay? So if we want to talk about that, so we're going to let sigma with a star on top of it be all the strings over sigma. So an example of this would be 0, 1 star. That is all binary strings. Another example would be zero. Yeah. So A, B, C, D, etc. I don't want to write them all out. Up to Z star. So that's all alphabetic. I guess lowercase words. So we can talk about that all binary strings, for example, but in general, if we have a set, we can put a star on top, and then that's just all strings with elements in that set. So 0, 1, all strings with 0 or 1 in each place, and the other one is a letter in each place. Okay, so let's actually talk about how to actually compute something. So how did the DFA actually compute? So these are DFAs up here. Look at the string 000 from before. How did it compute that string? Or say yes on that string, I guess. How did it do that? Well, where did it have to start? What state? Start state, I hope. And then what happened at each point along the way? Well, we followed the transition with that character, right? So we looked at the first character and we said, oh, let's follow the transition labeled that. Then we arrive at a state. Then we looked at the next character, figured out where to go from there. Then we looked at the next state and figured out where to go from there. Well, let's see. How did we know that we were done again? Well, do we have to end at a final state? We used up all the input, right? So once we use all the input, we either end up at a final state or we don't, right? And then that last check will determine whether that string is part of the strings that the DFA says yes on. So let's make some more definitions. So a language is a subset of sigma star. So sigma star, remember, is the set of all strings you could ever generate over sigma, and a language is just a subset of that. That's all it is. Another way you can look at it is a language is a set of strings. So just a few last things. Can a language have infinitely many strings in it? Yeah, so think of all binary strings, for example. That has infinitely many strings in it. Can a string be infinitely long? No. So a string, remember from 243, I hope, is a finite sequence of characters. So all strings are finite, but a language could be infinite. Okay? So an example that we had before was all the strings in 0, 1 star such that the length of W is odd. And we saw that this can be recognized by a DFA. I'll define what the term recognized means next time. But because of the example, we could have a DFA accept exactly the strings in this language, the set of all strings that have odd length. Any last minute questions?
What was the answer to the question you asked?
Which one?
Can the set of strings be zero?
So the technical answer is yes. Sipser says no. So I'll see you all tomorrow.